So in the last video, we introduced the Impulse-Momentum Theorem and discussed how you can use it to do things like estimate average forces in hammer hit situations. But now we're going to go with what it's usually used for, which is conservation of momentum. So to go down this road here, you need to define two terms. So you need to define the term system, which is a term we've been sort of using without a proper definition, but now we need a better one. And the system is simply the collection of particles under study. Okay. And then I also need to define an isolated system. And this is a system where the external force acting on it is zero. Okay, so let's see where this takes us here. So as a bit of a working example here, let's just think about a system of three particles. I'll say M1, M2, and M3. And so I can just decide I'm interested in those three particles and want to think about them as a collective. So there we go. I just draw a box around it, and I've now defined those three particles to be my system. Now, these particles are doubtless feeling multiple forces acting on them. For instance, they're probably interacting with each other. So let's say they're, at the very least, they're interacting with each other gravitationally, right? So there, oops, here, let me change the color. There we go. So there would be, say, a force on particle 1 due to particle 3. And over here, there would be a force on particle 1 due to particle 2. Here, there would be a force on particle 3 due to particle 1. Here, there would be a force of on particle 3 due to particle 2. That should be pointing more closely to there. Okay. Here there would be a force on particle 2 due to particle 3. And here there would be a force on particle 2 due to particle 1. And in addition to that, conceivably there are forces from outside the system that are acting on each of these particles. So let's just go ahead and start drawing them in. Well, we'll say this is the external force that's acting on particle 1. This is just due to stuff outside the system interacting with it. Same thing over here, maybe the force on particle 2 from the outside world is pointing like that. And then let's say on particle 3, maybe it's doing something like that. So the beauty of this is that when I'm trying to describe the net force acting on my system, it turns out to just be the sum of the external forces. Because what we're doing is we're just saying we're treating each of these as particles. So to find the net force, we're just going to add up all the forces, just like we always do. And if we had more than three particles, we'd keep going. But then, and I'll just stick this in parentheses here and in a light color. we would have also had a whole bunch of terms that look like this, because we'd have to go through, I mean, these are all forces acting, right? We would have to add all these up. So let's do that. So you'll have an F13 plus an F31. And then similarly for the other pairs, you would have a plus F23 plus an F32. And then you'd have, say, an F12 plus an F21, and so forth. Now, the thing is, with all of these, let's look carefully here. This F13 and this F31 are an action-reaction pair. Actually, let's leave it with the colors like that. So this means that since they point in opposite directions, F13 plus F31, that's 0. Similarly for F23 and F32 being an action-reaction pair, since they're equal in magnitude but opposite in direction, when you add them up, it goes to 0. And similarly here, that's an action-reaction pair. You add it up, you go to 0. And this will always work through, no matter how many particles you have, all of the internal interactions within the system cancel out. This is why, for instance, when we were doing the bit about cleverly choosing coordinates, cleverly choosing our systems, when we were looking at things like, say, the forces between cars on a train, we learned that creating a collection of systems that were all nested was easier. This is why we don't care about the details of the forces that hold things together. After you define the system, the net force is going to be the sum of all the forces on all the particles, but all those internal forces, because of Newton's third law of motion, will cancel out, and we're just left with the external piece. Okay. And it seems sensible enough, following the lead here, since this is what you have to do to talk about the net force on the system, it seems sensible enough to define the total momentum of the system, P tote here, to be P1 plus P2 plus P3, and if there's more than 3 particles, you just keep going. So you add up the momenta of the particles. And by the way, the plural of momentum is momenta, not momentums. That sounds like some sort of an antacid or something like that. So now here's the big deal. If we have an isolated system, then that means that the net force on the object is 0. Notice this does not mean that the external forces are 0. All it requires is that the sum of the external forces be 0. So if the net force is 0, then that means that over whatever time interval we care to think about, the impulse on the system, the net impulse on the system, is also 0. That means, by the Impulse-Momentum Theorem, that the change in the momentum of the system is also 0. Or a more useful way to write it is to say, if the system is isolated, the total momentum after the collision is equal to the total momentum before the collision. So let's work through some examples of how this might be useful. Most of the time where this is going to be really useful is when you're looking at things like collisions. You know, if you say you have 2 cars collide or something like that, to do it right, if you're an automotive manufacturer, you're going to have to fire up some pretty serious computer simulations to try to model the cars as a huge collection of individual masses and look at the interactions between all the individual masses. So if you need to know exactly how the vehicles are going to crumple in a collision, that's the only way you can do it. But if you're just interested in, say, two cars collide, how fast is the wreckage moving after the collision? Here's where the impulse-momentum theorem can be handy for us. The trick is to make an isolated system. So this kind of collision I just described, two cars getting into a wreck, that's something that we call, or at least I call, a sticky inelastic collision. Inelastic refers to the fact that energy is not conserved in the collision. Since we haven't defined energy yet, basically, if the objects deform, or if there's heat generated, or if you make a bunch of sound, or something like that, that makes the collision inelastic. When we get to energy conservation, we'll worry about elastic collisions at that point. But for now, we'll just focus on inelastic collisions. So let's say you've got two cars. Got a fairly lightweight car here, say 500 kilograms. That's a pretty light car. Let's also say that it's going at a absolutely ridiculous speed of 200 meters per second. Hey, that is race car kind of speed, so could happen. And then let's say it gets into a head-on collision with a much more massive car. Let's say this one has a mass of 1,000 kilograms. And let's say it's also going at 200 meters per second. Now notice here I put in a minus sign. I put in a minus sign here because it turns out that when you're doing these kind of collision problems in one dimension, it'll be different when you do it in two dimensions. But when you do it in one dimension, I find that it's more convenient if we go ahead and purely keep track of the directions when we put in the numbers. This is something called implicit signage. Up to this point, we've been assigning directions when we write the letters. That's called explicit signage. Here, we'll put plus signs in front of everything, and we'll sort out the directions when we actually substitute the numbers. That's implicit signage. We'll be working examples of that to show how that works. So this is what's going to happen before the collision. After the collision, what we have is one big tangled mess of metal here. And we know since the big car's going to quote-unquote win, the whole thing's going to go skidding off to the left. So we can already intuit that. And we just want to know how fast it's going. So here we have one particle. We have two objects before the collision. And now we just have one object after the collision, whose mass is m1 plus m2. So 500 plus 1,000 is 1,500 kilograms. And this is the beauty of this kind of analysis, is it is okay for the number of objects to change. The trick is we'll just add up all the momenta before the collision and all the momenta after the collision. And as long as the system is isolated, those two will be equal, and we can exploit that. So now what we have to do is actually make an isolated system. So if I go and draw a box around this, okay, I have made this my system, and then afterwards my system is just the one particle. If we look, say, the usual trick we'll do is we'll look like immediately across the collision. So just before they collide to just after they collide. So they haven't really, during that very short time interval, they aren't really skidding. And so we can neglect any forces due to friction horizontal on the cars or the mass of metal afterwards. So then all we've got left are normal forces up and gravity forces down, but those are always equal. And so when you add it up, you do indeed get that the net force on the system is 0. Now, between the vehicles, oh, heck no. When these things collide, there's going to be enormous normal forces, but by having said that both vehicles are the system, I make those normal forces internal, which means I don't have to worry about them. Okay, so with that, we can now go ahead and figure out what our final velocity of our twisted mass of metal is. So since we've established that the system is isolated, that will allow us to state that the total momentum final is equal to the total momentum initial. And momentum, remember, is a vector, so we need to take components. So here I will go ahead and say we're taking the x component here. So afterwards, it's just one object, so we'll just say P final x, and this will equal P1 initial x plus P2 initial x. But hey, they're all moving in just the x direction, so we don't have to worry about continuing to write x subscripts. So we just write down what this is. Afterwards, there's one object, mass m, velocity v final. Now, here I am not writing a minus sign in front. Even though we know that it's going to the left, and this is again because we're making the choice to use implicit signs. So when I solve for it, I'll get a negative number, and that negative number will give me the direction. So this is the same kind of thing like when we were doing kinematics. That was implicit signage there. We're bringing it back here for momentum. Okay, so then the momentum of car 1 before the collision is just m1 v1. And car 2 before the collision is m2 v2. All right. So to get the final speed after the collision, we just divide through by m. So v final equals m1 v1 plus m2 v2 over m. And we can put in our numbers. So we'll get that the mass 1 is 500 kilograms. And for V1, we'll put in 200 meters per second. It's going to the right, so it's positive. Now for mass 2, that was 1,000 kilograms. We have to put in negative 200 meters per second. And that minus sign is because it was going to the left. So we take care of the direction when we substitute the numbers. And then the mass of the wreckage afterwards is 1,500 kilograms. So when you crunch the numbers, what you'll get is negative 67 meters per second. All right, and again, we interpret the minus sign that we get now as meaning that the wreckage afterwards is moving to the left. So in this case here, let's check to make sure that this is plausible. Well, given that these cars are moving ridiculously fast, the whole problem's a little bit of a stretch, but race cars can't go this fast, so I'll take it. But our intuition, we knew that the big car was going to win, so you're sliding to the left, so the minus sign seems plausible. And we should also intuit that, the slowest you could end up with is 0. And there's no way that you could end up going faster than either of the cars afterwards. So as long as the magnitude is between 0 and 200, that seems reasonable there. 67 is between 0 and 200. So that looks plausible. Now, let's say you were to have an explosion. I'm not going to work an example of an explosion here just because I'll have a better one when we do two-dimensional momentum conservation. But an explosion would just be a case where the number of particles before the process was fewer than the number afterwards. We still treat it like it's a collision. It's just you start with, say, 1 particle and you end up with 3 or 10 or whatever. So it's still the same trick. The total momentum before and after, you just add up the momenta of the individual number of particles, and you don't have to have the same number of particles before and after. All right. So let's do another example here. Let's go and take a look at what I'd like to call a bouncy inelastic collision. So in a bouncy inelastic collision, the number of particles will stay the same. So let me just go ahead and steal some cars here real quick. There, it'll save me at least a little bit of drawing. Not too bad. So they're going to be the same cars. Initially here going the same speeds. So this is still 1,000 kilograms. Here now we'll call this V2 initial and V1 initial. That's the only difference we're really making here. And the reason now that we're keeping track of these as initials is because afterwards we're going to say that the two cars did not turn into a twisted mass of metal. Their bumpers did something anyway. So this car after the collision was measured as going at negative 20 meters per second. And so then the big question is, what's the final velocity of car number 1? Okay, so again, from our intuition, we expect it to go to the left because we expect the big car to win. And we expect that it should be going faster than the big car. All right. So with that, we can play exactly the same game. We go ahead and say, since I don't want to think about the normal forces between the cars, I will look at the split second before the collision and the split second after the collision and just make my system the two cars. So again, because we're looking at such a short time frame that the cars haven't had any chance to start skidding yet, we can neglect friction. So we don't have to worry about that. And again, we have normal forces up and gravities down. And again, they cancel. And so the momentum before so the systems are isolated because the net force on the system is 0. So since the system is isolated, we can just say that the total momentum final, I'll just write P final, equals P initial. All right, so then again, we can take the x component of this. So this will be P1 final plus P2 final. Again, we know this is all acting horizontally, so we don't really have to write the sub x's. Equals P1 initial plus P2 initial. So we can go ahead and put in what these are. This will be M1 V1 final plus M2 V2 final. This equals M1 V1 initial plus M2 V2 initial by the definition of momentum. Now we're trying to find V1 final, so we need to isolate that. So we'll have M1 V1 final equals M1 V1 initial plus M2 V2 initial minus M2 V2 final. Okay, we can do a little bit of algebra to clean this up a bit. We can divide through by m1, so this will give me v1 final equals v1 initial plus, and then here I can group out in m2. So I'll have m2 over m1 times v2 initial minus v2 final. All right, and again, we can go and put in the numbers, but remember, when you put in the numbers, you got to put in the plus and minus signs for the direction because we're doing implicit signs. So this will be 200 meters per second plus 1,000 kilograms over 500 kilograms times v2 initial, we said was negative 200 meters per second, and v2 final, so we have a minus from the algebra here, and then v2 final is minus 20 meters per second. So that's a minus, which is going to work out to be a plus. Anyway, you grind it out, you get negative 160 meters per second. Okay, that all checks. The minus sign again means we're going to the left, which we expected. We expected it should be bigger than 20 because we knew since the big car wins, the little car is going to go flying away from it. And we also intuited that it should be less than 200. So that all checks, and we feel pretty good about it. Now, before I get into my last application here, since I did promise throwing in asides about Noether's theorem as we go along, and it is certainly worth looking up Emmy Noether. She's a fascinating character. Fascinating person. In this case here, the reason that momentum is conserved, what she was able to show, is that it's because the laws of physics are the same in every location in the universe. So that's the symmetry there. So the laws of physics are the same no matter where you are, and as a result, per Noether's theorem, the momentum is a conserved quantity. Okay, so where I'm going to finish this out with is what we call partially isolated systems. So, as an example, let's say you've got a track here, and you've got a cart rolling along the track. And just to give a nice concrete number for this, let's say it's got a mass of 1 kilogram. And let's say the cart is moving initially at 10 meters per second. So when it gets over here, what happened to it was a blob of putty that had a mass M2 of 1 kilogram. Oops. There we go. Fell and landed onto my cart. So afterwards, the cart goes traipsing off. And I would like to know, what is V final for this? Well, this is definitely a sticky inelastic collision. The question is momentum conserved here? And the answer turns out to be no. This is because for the momentum of the system, this had a momentum pointing to the right. This had a momentum that was, say, initially 0 and kept increasing as it fell down. So the total momentum of the system started out rightward and then started angling down and right. But then afterwards, when the putty collided with the track, now it's going just again straight to the right. So this meant there had to be upward forces acting on our system. So, let's go ahead and say our system is the cart plus the putty. But the problem here is that there's a normal force of the track up that has to overwhelm the force of gravity down in order to keep the cart plus putty from crashing through the track. So this is not isolated. However, it's only not isolated in Y. As long as there's no friction, hey, these are dynamics carts, the very low friction. This is isolated in X. So although we cannot say that momentum is conserved, that would be incorrect. It is not correct to say that P final as a vector equals P initial as a vector. In this circumstance, that would be wrong because the system is not isolated. Because the X component of, since the system is isolated in X, or no X components in force, it is impossible for the X component of the momentum to change. So although we can't say that the Y components of the momenta are equal before and after, because they're not, we can say that the X components are equal. So afterwards, we can say, all right, this is mv final equals m1 v1 initial. So that gives me that the final velocity is m1 over m v1 initial. So putting in what these are, this was 1 kilogram over 2 kilograms times 10 meters per second, we get 5 meters per second. So if you actually try something like this, if the masses are equal, you'll see that the speed of the cart drops to half of what it was before. So momentum was not conserved in Y. There were external forces on the system that were not balanced. So it was not isolated in Y, but we could still exploit the fact that it was isolated in X to demand that the momentum was a constant in X. Okay. In the next series of videos, we'll start to take a look at what happens when we treat this in more than one dimension. Catch you on the flip side.